Here's a common moment in enterprise AI. A team builds a chatbot on a general model. It talks well, but it keeps getting company-specific details wrong, or the tone doesn't match the brand. The question comes fast. Should this be fixed by fine-tuning the model or by feeding it better information? Fine-tuning is the practice of taking a model that already knows a lot about language, then teaching it, gently, how you want it to behave for your task. It's like giving a great generalist some focused coaching. The model's core abilities stay intact, while its habits shift toward your needs. There's another common approach called retrieval-augmented generation, or RAG. That means the model reaches out to external sources, like your documents or databases, at answer time. It doesn't change the model's internal weights, it simply brings the right facts into the conversation. The big difference is this. Fine-tuning changes the model's behavior. Retrieval changes its access to knowledge. One is about shaping how it responds. The other is about giving it the right information on demand. Why care about the distinction? Because it affects cost, reliability, and speed. Fine-tuning can make responses more consistent, more concise, and better aligned with style or policy. It can also reduce how much prompt engineering is needed. Retrieval is better when the gap is missing or changing facts, like product specs or legal policies that update frequently. Choosing well can save months of effort and a lot of money. Think of a pre-trained model as a versatile chef trained on global cuisines. Fine-tuning is a short apprenticeship in your kitchen, where the chef learns your family's recipes, plating style, and preferred level of spice. The chef doesn't learn brand new ingredients. The pantry hasn't changed. Retrieval is like handing the chef a recipe card or a new set of ingredients at the moment they cook. The chef's habits remain the same, but the dish includes the exact items you supplied. So the simple version is, if the model talks generally, but not exactly the way you want, fine-tuning helps. If it lacks the facts, retrieval is the tool. Now, what actually happens during fine-tuning, and what changes inside the model? Start with a base model that's already pre-trained on large amounts of text. Pre-training gives it broad language skills, how sentences flow, common patterns, and a lot of surface-level knowledge. Fine-tuning picks up from that point using a smaller, carefully curated dataset that shows the specific input-output behavior you want. This is often a few hundred to a few thousand examples, formatted as prompt and ideal completion. What matters here is the quality of those examples. Clean, diverse, and correct pairs act like demonstrations of the exact behavior you're aiming for. If the examples are messy or contradictory, the model learns those habits too. In other words, fine-tuning is the world's most literal apprentice. It imitates what you show it, good and bad. The first training phase is supervised fine-tuning. The model reads your prompt, predicts an answer, and compares it to the target answer from your dataset. When it's wrong, the training nudge adjusts the internal weights slightly, so the model is more likely to produce the desired phrasing next time. These adjustments are subtle. The learning rate, the size of those nudges, stays small to avoid overriding the model's core knowledge. The key idea is that fine-tuning shifts the model's probability landscape. Certain words, phrases, and formats become more likely in the context you care about. If you want structured answers with bullets or JSON or a steady professional tone, the model becomes more consistent at doing that. If you want it to prefer citing a policy paragraph number when answering a returns question, you can teach that preference. Sometimes, supervised training isn't enough to capture nuance. That's where preference optimization helps. Methods like reinforcement learning from human feedback or direct preference optimization take multiple candidate answers for the same prompt, rank them, and teach the model to prefer the ones that are safer, clearer, or more on-brand. Put differently, it's coaching the model with examples of this one, not that one, to refine judgment beyond literal imitation. To make this concrete, consider an e-commerce company. The team wants a chatbot to handle returns questions. They start with a capable base model and gather 1,000 internal support chats that show great responses. Each example is cleaned and formatted. A customer question, then the ideal agent answer that's policy accurate and polite. After a short fine-tuning run, think hours, not weeks, they run a pass of preference optimization where human reviewers pick the best of 2 or 3 candidate responses for tricky prompts. On a held-out test set, relevance goes from roughly 2/3 to over 90%. The bot doesn't need heavy prompt instructions to stay on tone, and the answers come out structured in a way that drops straight into the ticketing system. The training cost is small compared to building from scratch, and there's no need to retrain the model every time inventory changes. When the return policy itself updates, the team uses retrieval to insert the newest policy text into the prompt, keeping facts fresh without changing the weights. So what changes with fine-tuning? Behavior, format, style, and task-specific habits. What doesn't change? The model's store of factual knowledge in a way that reliably covers new data. That's the job of retrieval, or in some cases continued pre-training on large corpora, which is a different, more expensive process. There are limits to keep in mind. If the dataset is too small or noisy, the model can overfit, memorizing quirks that don't generalize. That shows up as great training performance, but shaky results on new examples. Monitoring a validation set where you do not train is how you catch that. If the validation curve stops improving while training keeps getting better, it's time to stop or to add better data. Also, fine-tuning can unintentionally shift safety behavior. If your examples include edge cases with harsh language, the model can adopt that tone. Guardrails should be baked in, and safety checks should be part of evaluation. At this point, it helps to carry a simple mental model of what fine-tuning does. Imagine the model as a giant mixing console with millions of tiny knobs that control the likelihood of different patterns in different contexts. Pre-training sets those knobs to reasonable defaults. Fine-tuning reaches in and turns a small set toward your desired behavior. More of this tone, less of that phrasing. Always include a reference number here. Avoid speculative statements there. The music is the same language the model already knows. You're shaping the performance for your stage. Now, when should an enterprise choose fine-tuning over retrieval, or combine them? Start with the problem diagnosis. If most failures come from missing or outdated facts, prices, product specs, legal clauses, focus on retrieval first. Build a pipeline that ingests your documents, splits them into chunks, embeds them into a vector database, and retrieves the most relevant pieces at question time. The model then has the right ingredients, and you can use prompts to encourage citations. If the model sees the right facts but still answers in the wrong style, or drifts into unhelpful formats, or ignores required fields, that's a behavior gap. Fine-tuning helps here. It bakes those expectations into the model so you don't have to repeat detailed instructions in every prompt. Combining both is common. Retrieval supplies current knowledge, while fine-tuning ensures the answer style, structure, and decision boundaries match policy. Consider how this lands in real systems. In a help desk workflow, a fine-tuned model can produce a structured reply that includes a disposition code and a next action field in JSON. That reply can flow directly into the ticketing system with minimal post-processing. Latency improves because the prompt can be shorter. Costs often drop because you're not stuffing the context window with long instructions on every request. In a sales enablement tool, a fine-tuned model can be taught to write emails in your brand voice and to ask for a meeting in a specific, compliant way. Retrieval can still attach the latest product sheet and competitive notes in the background. The result is a consistent message that also reflects the freshest information. On devices or within tight budgets, parameter-efficient fine-tuning techniques become relevant. Instead of updating all the model's weights, approaches like LoRa add small adapter layers so you only train a tiny fraction of parameters. That reduces compute costs and lets you swap adapters for different tasks or brands without retraining the whole model. The base model stays the same. The adapters carry the behavior differences. Safety and governance integrate here as well. If your organization requires a specific refusal policy for certain requests, preference optimization can encode that preference, and a separate moderation pass can check generated outputs before they go out. Versioning matters too. Keep a record of the base model version, the fine-tuning dataset hash, and the adapter version in production. That way, when behavior changes, you can trace it and roll back if needed. Let's return to the e-commerce example and walk it as a practical flow. The team starts with baseline prompting and measures performance on a representative test set of returns questions. They track helpfulness and accuracy scores with human raters on 100 held-out prompts. The results are okay, but not reliable, and the tone changes from answer to answer. They add retrieval by indexing the returns policy and procedures into a vector database. Answers now cite the correct policy more often, and accuracy rises. However, the format is still inconsistent, and sometimes the model fails to include the required disposition code for the ticketing system. That pattern, repeating across different prompts, points to a behavior issue. They fine-tune on 1,000 cleaned examples, most of them short. Each example shows the ideal structure, such as including a policy citation, a clear action step, and the disposition code in a predictable location. They run a short training job with a small learning rate, then a preference pass where reviewers pick the answer that best fits brand tone and policy compliance. On evaluation, accuracy on the held-out set jumps from around 65% to 92%. The refusal behavior is consistent on disallowed requests, and the outputs drop smoothly into the system without manual cleanup. The training spend is modest, and future policy updates come in through retrieval, so there's no need to retune every week. The integration point is clear. Fine-tune once in a while to lock in behavior, use retrieval daily to keep knowledge current, and watch metrics across both. There are a few misconceptions to clear up. Fine-tuning is not the same as uploading your company wiki into the model. It doesn't inject an entire database of facts in a way that can be reliably recalled on demand. It biases the model toward behaviors and patterns that appear in your examples. For fresh or rarely seen facts, retrieval is much more effective. Another misconception is that fine-tuning is automatically better than prompt engineering or RAG for customization. In many cases, thoughtful prompting plus retrieval gets most of the way there. Fine-tuning is helpful when there's a stubborn, repeated behavior gap that prompts can't fix without becoming unwieldy. It also helps when you need strict format adherence, or when you want to reduce token usage by embedding instructions into the model's habits. There's also the idea that any data will do. In practice, raw enterprise logs are messy. They contain errors, inconsistent tone, sensitive information, and sometimes harmful patterns. If you feed that directly into fine-tuning, the model learns those issues. A small, well-curated dataset often beats a large, noisy one. If there are fewer than a few hundred good examples, consider holding off, augmenting with synthetic pairs reviewed by humans, or leaning on retrieval and prompt improvements first. What about evaluation? Numbers like perplexity are sometimes used in research, but they don't always reflect enterprise goals. A simple, reliable approach is to keep a fixed test set of prompts that reflect your real tasks and score outputs with human raters on dimensions you care about: accuracy, clarity, safety, and format adherence. Automate as much as possible, but keep a human in the loop for final judgment. If you can, track a validation set during training and stop early when the curve shows no improvement. That helps avoid overfitting and saves compute. Teams often ask about maintenance. Fine-tuned models can drift if the domain changes or if user behavior shifts. Set up a feedback loop where bad outputs are flagged and either routed to retrieval improvements or added to a future fine-tuning dataset after curation. Keep adapters or model snapshots versioned so updates can be A/B tested and rolled back, and store responses with the prompt, retrieved context, and model version so you can audit decisions later. Let's talk cost and latency for a moment. Fine-tuning a large model is much cheaper than training one from scratch, but it still requires GPU hours and labeled examples. Parameter-efficient methods reduce that burden. At inference time, fine-tuning can lower token usage because the prompt can be shorter. Retrieval adds a step to fetch documents, which increases latency slightly, but the net gain in accuracy often justifies it. When low latency is critical, consider caching results for common queries or pre-computing responses for frequent intents with a batch job. Security and privacy play a role. When preparing a fine-tuning dataset, scrub personally identifiable information and sensitive content. If logs contain customer data, anonymize it before use. Some vendors allow data to be used for training only within your account boundaries. Confirm those settings. For retrieval, set strict access controls on the document index so the model only pulls data the user is authorized to see. Now, here's a compact way to decide. Start with a baseline model and a small, representative evaluation set. Add retrieval if most failures are factual. If consistent behavior issues remain, tone, format, refusal policy, collect high-quality examples that show the exact outputs you want and fine-tune on those. For teams with tight compute budgets, use adapters. Throughout, measure with human ratings and a validation set, and stop training when the curve flattens. If the dataset is small, prioritize diversity of examples over raw count. 2 quick extras can raise quality. First, mix in counterexamples. Show the model how to gracefully refuse unsafe or out-of-scope requests. That prevents it from inventing answers under pressure. Second, teach the model the structure you need by example. If your downstream system wants key-value JSON with specific fields, include many examples that match that schema exactly. Consistency is learned. Put all this together and fine-tuning becomes a precise tool, not a blunt instrument. It shapes how a model behaves, so it performs reliably within your business context. Retrieval keeps the knowledge live and accurate. The combination is powerful. One trains durable habits, the other hydrates answers with the latest facts. Before closing, a final mental checkpoint. Fine-tuning is not a magic portal to perfect knowledge. It's a way to steer a capable model so it talks and formats the way your organization needs. Retrieval is not a patch for sloppy behavior. It's a pipeline to the right information at the right time. Use each for what it's best at, and let measurement guide when to switch, combine, or stop. If this helped, a like and subscribe helps us make more of these.